In this video, I want to just take a quick second to talk a little bit about function notation. Function notation is something you've seen for a while, and it should be very natural to you. But still, there are some ways that we use function notation in calculus that can be a little bit different than what we used in algebra or algebra 2, geometry, classes like that. And sometimes they throw students for a loop. So what I wanted to do is just take a quick look at some function notation and just make sure that we're all playing on the same ground rules. Because once we start getting into examples, hopefully this will be as natural to you as I hope it would be. And there are just a couple moments during this video when you're going to go, wait, what? Oh, yeah, sure it is. Okay, so let's see if we can make that voice come out of you. All right, so here we are on a blank sheet of paper. So let me think about the function f of x is equal to 2x plus 1. All right, so when we've got the function notation, this says that our input variable is going to be whatever x is, and the output expression here is just some expression. And if we substitute x in for that expression, we're going to figure out what f of x is equal to. This is how you're used to thinking about function notation. So for instance, if I said, what is f of 4? What would you say? Well, you substitute 4 in for this expression and you get 2 times 4 plus 1, which is 8 plus 1. So f of 4 is equal to 9. Okay, hopefully that was pretty obvious. Let's take a look at another example. Let me decide over here that f of x is equal to x. All right, so what is f of 3 equal to? Again, you're going to do the same thing. You're just going to substitute 3 in for x in this expression. In this case, there's no arithmetic to do at all. Your output is just 3. And what's f of negative 4? Again, you just substitute negative 4 in for x. There's nothing else to do. All right, so this is a function where the input and output are the same. Okay, our fancy name for this is the identity function, because whatever the output is identical to the input. All right, now let me give you one example that sometimes throws students for a loop. What do you think the output of these functions are? Well, we're kind of going to do the same thing. We're going to substitute 1 in for x in this expression, but there is no x in this expression. So what is this expression equal to? Well, this expression is equal to 8 when x is equal to 1. When our input is equal to 9, our output is equal to 8. When our input is equal to negative 974, our output is equal to 8. All right, so this is an example of a function that is just kind of looking, it's a little bit too easy to imagine. This is a constant function. Because the output value is constant. It doesn't depend on what the input is. Whatever the input is, the output is 8. All right, so that's an important class of functions to think about. All right, so identity functions and constant functions are both linear functions. So constant functions are always horizontal. So for instance, this function, if this is my x and y coordinates, f of x equals 8 is just the line y equals 8. The identity function is just the line y equals x. All right, and so you can see the connection between the function definition, and if we just replace f of x with y, we've got, the equation that we can graph on the coordinate plane. There's one last example that I want to show to you. Let's imagine a function f of x is equal to x squared. So what do you think we should do with this? So this is a little different in that the input is an expression. But we're going to do exactly the same thing that we're used to doing. We're just going to take wherever we see x in the expression for the output, we're going to substitute in whatever the input value is. So in this case, this is equal to a plus b squared. All right, and remember that if you ever needed to multiply that out, and we will before too long, you can either use the box method. So a times a is a squared, a times b is ab, b times a, I'd like to call that ab as well, just to keep the common terms together, and b times b is b squared. So adding all of these terms together, we've got, this is the only a squared term. We're going to combine those two ab terms to give us 2ab, and the b squared is its own term. The other thing you can do is, if we write this as a plus b times a plus b, we can use what's called FOIL. All right, and so this just gives us a little bit of a system to make sure that we're multiplying all of the things together if we don't want to use the box method. All right, and so the F in FOIL stands for first, the O stands for outside, and I'm betting you can guess the last two. The I is inside, and the L is for last. All right, so if I want to multiply these two binomials together, first thing I do is I multiply the first term of the two binomials. A times a is a squared, and now the outside pair, a times b is ab. The inside terms, these are the two inside terms, b times a, again, I'm going to call that ab. And then the last terms, b times b is b squared. And again, collecting the like terms, 2ab plus b squared. All right, so we get the same method whether we use the FOIL method or the box method. And sometimes we find ourselves using something like the FOIL method if we're multiplying something more complicated, like if I wanted to say a plus b times a squared plus ab minus b squared, for instance. All right, so if I wanted to do this in a coordinated way, making sure I don't forget anything, I can start with the first term of the first polynomial and the first term of the second polynomial. So a times a squared is a cubed. Now I'm going to go to the next term of the second polynomial. A times ab is a squared b. A times negative b squared is negative ab squared. And now that I've finished the second polynomial, I'm going to switch to the next term of the first polynomial and go back to the beginning of the second polynomial. B times a squared, I want to keep my letters in alphabetical order. So that's going to be plus a squared b. B times ab is positive ab squared. And b times negative b squared is negative b cubed. All right, and then I collect my like terms together. I've got just one a cubed term here. I've got an a squared b and an a squared b. So that's going to be 2a squared b. I've got a negative ab squared and a positive ab squared, so they cancel each other out. I don't have an ab squared term at all. And then minus b cubed. So the product of this polynomial is right there like that. Okay, hopefully all of that made sense. If not, just sit down and kind of watch this video at half speed and do a couple problems of your own that are like it. If you want help practicing with some of these techniques, drop me a line and I can find an IXL that would help you brush up these terms. But being able to multiply out terms like this, if you want to use a box technique, you can absolutely do that. That will save the day. If you want to practice kind of a foiling technique like this, this will come up from time to time. So it's a nice skill to have under your belt. But the basic idea I want you to think about is not so much the algebra of what I just did, but how to think about evaluating function notation when we have odd things like constant functions, where the output does not contain our input variable at all, and functions like this, where we're trying to express a function at an expression instead of something like f of 4 or f of x. Having an expression in there just means that we're going to substitute that expression in for our input variable. Okay, so hopefully if you've got these under your belt, that will make the next bunch of examples seem a lot more comfortable to you.